So if I mute you, it's not, I'm being impolite, I just want to minimize the background noise. Cool, but when we get to question and answers, you know, feel free to unmute yourself. Awesome. Welcome everyone. This is our 5th coding challenge. Thanks everyone for joining. We are Deep Learning Adventures, a fun and engaging community where we use deep learning, machine learning, and other statistical approaches to tackle interesting problems. My name is George, and I'm joined today by my great friends and colleagues, David, Robert, and guest speaker as well, and guest friend as well, Dmitry, who has been contributing a lot lately to our notebooks, and really excited to have him here on this coding challenge as well. If you join us for the first time, we're on a meetup. If you Google meetup and Deep Learning Adventures, you're going to find us there. You can also find us on YouTube. We have a playlist. We actually have 2 playlists. The first one that is an introduction level series on TensorFlow, tackling various challenges like computer vision, natural language processing, time series forecasting, as well as a fun and engaging interview with Lawrence Moroney, the AI lead at Google, who also authored the TensorFlow in Practice specialization that we took a couple of months ago. Recently, we've embarked on a 5 coding challenge series. We tackled computer vision, we tackled NLP, we tackled annotation, structured data, and today we're going to see some applications using time series forecasting. Just some quick thank you notes to different meetups that also cross-posted this event, the Machine Learning Paper Club, a meetup in the DC area where we go over different papers and study their findings. Also, the Bethesda AI meetup has cross-posted in the past and continue to do so. Some of our events, a great meetup as well. Data Education DC as well as Upskill ML, 2 great partners of ours who have helped us spread the word about our meetups, as well as the greater mission of spreading knowledge to the community, as well as at a global level. As you've probably seen online, we have people joining us from all around the world. And lastly, we have been advertised on Hatchpad, which is a local community where you can find jobs. You can also learn get an insider perspective of what kind of a technology stack they use, what is the culture like in a company, so that if you're interested in exploring new roles, you can have more of like an insider view. Cool. I'd love to do some kind of introductions, but given the fact that we have 4 notebooks to go together, and we won't have much time to do so. So again, if this is your first time, welcome, and happy to get to know you better, hopefully in the next session or maybe in our next happy hour where we just get to know each other better and form a stronger community. We use Coursera and Deep Learning AI materials in the past. I don't think we're using it this week. Just a slide here to acknowledge them. The main tool we'll be using is TensorFlow. You can explore other tools as well. We've used TensorFlow as the main machine learning and deep learning platform for us. And in terms of setup, you don't need a very expensive computer or anything else. You can just use Google Colab, which is basically a free Jupyter notebook that's hosted on Google Cloud. Great. So as I mentioned, we've tackled the computer vision problem in the past, trying to identify healthy and unhealthy plants. We did an annotation episode where we tried to assign emotion to different dialogues from the popular TV show, The Big Bang Theory. Then we used a larger data set where we tried to predict what is the emotion behind each line from another popular TV show, Friends. And last time we tackled a structured data set where we had 30 plus features and a very highly imbalanced data set of fraud and non-fraud transactions. We had about 250,000 transactions and about 400 or 500 of them were fraudulent. Cool. Today, to finish this marathon of coding challenges, we're going to do time series prediction. We will use actually weather data from an airport in Madrid. We'll use machine learning, deep learning, as well as statistical approaches to do prediction. Cool. Let me fast forward to the appropriate slide. Right here. So I'm just going to talk a little bit about the data set, and then Dmitry is going to talk about his approach and how he handled this challenge and some of his findings and lessons learned. Then I'll share some notes from my notebook, and David, and then Robert. So this data set is from Madrid, has data from 1997 till 2015. It's a daily level data set, meaning you get one metric per day. And if you see here the structure, it has about 3 metrics per, or 3 numbers per metric, I would say. So for example, for temperature in Celsius, we have maximum, average, and minimum. For dew point, for humidity, for pressure, for visibility, for wind speed. We have 3 metrics. We have as well precipitation, how much rain did it cover the area, what was the cloud cover. Then we have another feature called events. As you'll see, it contains information if it was a rainy day, if it was foggy, if it was windy. You'll see more in details. And here in this visualization here, you have a very simple chart of how does the average temperature in Celsius look like from 1997 all the way to end of 2015. Cool. That's just some basic information about the data set. I'd love to hand it over to Dmitry and ask him to share with us his approach and his findings. Let me make you host.
Before you continue, can you give a brief explanation of the prediction task? So I assume you're predicting like the temperature for the next day. I assume you aren't given the temperature from the next day, because then like if you know, or sorry, you don't, or sorry, I assume you're not given like cloud cover for the day you're predicting for, because that day hasn't happened yet, right?
Yeah. Yeah, actually that's the very beginning of what the notebook is about. So yeah, the very basic challenge we had was daily prediction for the last 3 years of this data set of average temperature. But there were some other tasks, given time. If we had more time, we could explore other things as well. But the main task was univariate prediction using only average temperature. Historical information, can we predict the last 3 years of average temperature in Celsius? And that was the univariate case, meaning we can only use that field. There are other approaches, other tasks where you can use other fields as well, so multivariate. Cool, Dmitry, you should be able to share your screen, and
oh, okay.
I made you host.
Sorry about that.
Host.
Okay. Can you see my screen?
Yes.
So in the interest of time, I will go through the data wrangling and EDA pretty quickly to have more time for the models. So let me make sure I'm on the right. Sorry. Yep. Okay. Yeah, this is it. So just very quickly, as you said, George, this is a daily data with a few groups. There is the temperature, humidity, dew point, and some other variables. So first thing I did, I just renamed the columns to make them more comfortable to work with. Then I just explored data visually, and like the first thing we see is that the temperature is whole numbers, which is apparently enough for airport purposes. But if we think about the prediction, we will predict floating point, and so that already introduces some error, which must be on the order of quarter degree Celsius is already there. We see there are quite a few non numbers, and we'll have to deal with the missing data here. just visually, again, see, look at the ranges and describe the variables. And you know, the key measurements come in triplets: the maximum, minimum, and the average. And so, as we will see later, I mean, I decided, you know, the maximum, minimum being redundant, and I just removed them from my analysis. I think they more like introduce noise as opposed to any meaningful information. So then I checked the dates, and what I found is there are some gaps in the data. There is almost half a year missing in 2000 and some data later. So the contiguous daily data starts from February 1, 2004. And so I decided it already gives like almost 12 years of data. So this must be enough to make a meaningful forecast. So I just left that part. Then I quickly went to impute some of the missing parts. Like visibility seems to be related to humidity and temperature. So I thought, you know, just instead of throwing that out, let's impute with something. And the best I could do is impute with the mode, which I think the visibility number 10, whatever the units are, I'm not sure, but 10 is the most frequent, so I just replaced all the nans with number 10. There are a few gust speed and cloud cover, a few variables that I don't think are you know, predictive or informative for next day's temperature, and also, you know, the patterns of how they're missing. I couldn't, you know, make sense of them, so I decided to just remove them. This is interesting, the precipitation. This is events. Yeah, events is basically all kinds of, you know, fog, rain, snow, etc. But the tags are very imbalanced, and there are a few rows with just one observation, etc. So I just decided to convert this to a rain, no rain situation. So there are a lot of observations, a lot of tags with rain inside. So basically, I converted this to rainy day or otherwise. And that's it. So the data, the imputation is done. I visualized a few series, as we can see, you know, and I'll show it later. There is already, you know, if you just do a simple linear regression, there is already 0.13 or 0.14 Celsius per year upward trend, which is almost like visible here. So this must be global warming or something else, but there is, you know, the temperature is rising. And here we can see that the minimum and maximum temperatures are basically forming these bands around the average. So this is why, you know, I just visually decided it shouldn't add much information. So the same with humidity and some of the others. So I just removed this mean and max. And then we are left with this, oops, sorry about that. We're left with this relatively compact database, which covers, you know, as I said, 12 years of daily data, temperature, dew point, humidity, pressure, visibility, wind speed, whatever information that may have, precipitation, rain, and wind direction. So this is basically what I work with, this data. I just then went to just visually represent some of the variables and see if they, you know, make sense basically, which they do. You know, dew point is related to temperature and inversely related to humidity. So, but I didn't sort of infer much of insights from here, just visually to understand what's going on here. Okay, so here is, this is already something that is already telling us something. Temperature is positively correlated with dew point, of course, and inversely related to humidity. And as we will see later, I visualize some of the feature importances. These are basically the key three features that come up very often: temperature related to dew point and humidity, but not much of anything else. I think there is some predictive power in wind speed. Apparently, winds are stronger in winter time or something. But for example, wind direction, rain, precipitation are not very telling. So this is what I set out as a workflow. As you said, George, so we can predict basically any of these variables, taking the others as predictors. It's just temperature seems to be, the most reasonable target. But the same analysis can be done for anything else. And also, again, we decided to do daily, but we can do weekly forecasts, etc. So I decided to use temperature and 1 day ahead forecasts. And mean absolute error as our metric. So then, because it's a time series prediction thing, it's very important to protect against all kinds of data leakage, so that the actual data does not inform your predictions. So basically, it's very important to split the train, validation, and test so that they don't overlap at any point in your analysis. And also, what I also used is basically I distorted intentionally the last observation, and at inference time, if your forecasts seem unusual, then you have a data leakage. So it's a quick way to diagnose if the data leaks. And actually, I had that problem, with ARIMA from the stats model. There was a new package for me, so first I implemented that, and there was a data leakage. So this trick helped me. Then I used four different. Let me switch to another notebook. Yeah. So I used 4 different models: ARIMA, XGBoost, LSTM, and I also used linear regression to see, how they relate to each other. And yeah, this is another notebook. Yeah, so as you suggested, George, I took the last 3 years as a test period, and last, about half a year as a validation for my models. So the first thing we do is establish a benchmark. So the naive forecast that just, or they call persistent forecast, also basically forecasting tomorrow as today, is especially when the signal to noise is low. It's a very powerful benchmark, and it's basically not easy to beat. So first we have to establish that. This is how it looks, basically shifted 1 period ahead. And the mean absolute error is 1.5, which I think George explains this ceiling that you described. So this is basically what we're fighting against. Basically, any model should be better than this. I also tried this thing called moving average difference forecast, which is basically the simplest way is forecasting the difference between today and tomorrow as the same as the difference between the same dates 1 year ago. And when the period is strong, so to speak, and the volatility in the daily data is low, then it's a powerful forecast. But in this particular case, it's the other way around. So using 1 year ahead, 1 year ago observations only introduces more noise. So it didn't work in this case. So this is, I just tried, the best I could do with this moving average is 2.14. So I didn't even include that in the reports. Then I just used linear regression, and I should say, I started with univariate analysis, in my previous version. But then I figured out, whatever I do univariate, I can't break the naive forecast. It's just, the best I could do is naive forecast. Even with LSTMs and, other powerful models, if all we have is temperature, the best univariate model learns to predict the naive forecast. It can't do any better. So I just decided to not repeat all of that here and just take work with the multivariate data straight off. So I just take so all of the predictors, and I choose the best window on the validation set, and it happens to be 7 days for some reason. So I fit the regularized ridge regression on that window data set, and this is what I get, basically 0.42, which is better than the naive forecast, and it looks like this. Some parts sort of repeat the naive forecast, like for example here it's shifted to 1 period here, but some other parts are not exactly repeating the pattern. Then I visualize the feature importance in the linear case, which is very easy to do. And what we basically see is that the most influential feature is last day's temperature. Then some influence is the dew point, last day's dew point. Some other probably I didn't include the standard errors, but you could see that this tail is basically irrelevant, and all of the information is just 1 day or maybe maximum couple of days before. Why in this case the best model was, as I said, 7 days ago? That's a separate question. That if I had more time, I would explore. Why exactly pick the 7-day window. Yeah, and this is I just summed the feature importances across the days, and of course the 80% is explained by the temperature, but there is still some predictive power in other features. So that's why I think this helps explain why the univariate is weaker than multivariate, because there is clearly some predictive power in these other things. So with ARIMA, I tried a few different things. First I was sort of I went the wrong way. I thought this should be automatically 365 days SARIMA, which seasonal difference, but that was the wrong approach, because the seasonality, as I said, just takes away the explanatory power, just introduces more noise, and that's why I just stayed with 1 day difference forecasts. I mean, as any data which is quasi sort of continuous, and the measurements come close to each other. So basically, the process that has inertia is basically autoregressive, meaning tomorrow's forecast is not far from today's temperature, and we can see that on the partial autocorrelation plot. Just 1 day is the yesterday is the strongest predictor, but we also see down here some predictors like 2, 3, 4 days before, whatever the effect may be. Again, but that's a cumulative sort of effect on today's temperature, and again, this tells us there is autoregressive process, and we should just go ahead and try to find the best configuration by grid search, which I did. This is just to visualize how they're distributed, and thank God this is not anything but normal. There are different data, and they come in this ladders because this is the integer temperatures basically. So then I thought, okay, we have this 7 days window in the linear regression. Let me try a few configurations with this window, and I found that the best configuration is this 711. And again, I tried that, pretty much the same, 1.42, and this is how it looks. ARIM also has the confidence intervals for the features. I thought it would be interesting to compare to the linear and some XGBoost that I did later. So this is the coefficients of the temperature, dew point, and wind speed, and this is pressure. So these four are around 0. I think we can confidently ignore them. But temperature and dew point are, of course, very strong predictors, and these two are, suspects, pressure and wind speed. So with XGBoost, again, didn't do like a full-blown grid search of hyperparameters, just tried a few depths of the iterations, and again, pretty much the same ballpark, 1.42. But this one, XGBoost, doesn't look like it picks up this naive forecasting pattern. Just maybe a couple points here and there, but generally it tries to do something different than the naive forecast. And with XGBoost, this is the feature importance again. We don't see any influence, at least visually, don't see any influence of anything else but the temperature itself. But when we look at the numbers, temperature is, of course, 86% is the bulk, but it's not like 98 or 99. There is also some information in these features. It's just we can see this on this color map. So this is more like just to confirm that we're on the right track, and see that the most influential feature is the last day's temperature, which is the basic AR1 process. And some strange patterns I saw, in some other places, this gaps like, the day before and then 4 days before and then 7 days before for some reason. This may be some autoregressive artifact of that specific data, or maybe something else. I don't know.
Dmitry,
Yep.
couldn't the 7 days be day of the week? So I've heard that the traffic patterns has effect on temperature, on weather. So the fact that there's no rush hours on Saturday and Sunday to speak of could give
that's a cool observation. Yeah, that's very well maybe the case. I didn't think about that, but that's pretty cool. Yeah. So maybe that's why the window that the linear regression also picked was 7. That's very interesting.
Is it because of pollution you're thinking, Kathleen, or because of?
Yeah, well, actually, the traffic, that there's rush hour and that it wouldn't have to be pollution, but just the temperature is higher when there's all those cars driving around the cities.
Yeah.
This is at the airport, right?
Yeah, that's the airport. Yeah.
Yeah, so airport traffic may differ.
Yep. So with LSTMs, with neural networks, and I think you guys have tried a lot more different architectures, so I'll be just very quick here. I only thought about comparing multivariate versus univariate structures, so didn't do much of a hyperparameter search here, but basically I just thought, like throw a very powerful model. Of course, we don't have enough data for 500 unit LSTM, and this is overkill for this data. But I just said, let's just quickly do something very powerful and see where we land. And this is what I got. The interesting part is what was interesting for me was that TensorFlow allows the mean absolute error to be your loss function, which I didn't realize. I thought MSC was I should use MSC, but MAE is also a loss. So apparently, the fact that it's not differentiable in the zero, that the kink doesn't prohibit the algorithm from running. Basically, this is the training history. It converges pretty fast, that's the result I got in the same ballpark, 1.3, 43, 42, basically in the same ballpark as the others. And this also looks, close to the previous forecasts. Again, this is, shifted, seems to be shifted one day in many places. And finally, I just tried the same thing, univariate, with a smaller model, and the picture we get is almost exactly naive forecast. It's just exactly the same curve shifted one day ahead. So basically, my sort of conclusion from here is that basically the univariate model, the best univariate model is learning to repeat just the previous day. That's as well as it can do. And then when I have this collection of different models, and just to repeat, so this is naive forecast, ridge regression, ARIMA, XGBoost, and 2 neural networks. What I thought is would be interesting to see how they correlate these forecasts. We don't work with the naive and univariate because they seem to be significantly worse. But these 4 in between would be great to see if they're correlated, and if they're not perfectly correlated, maybe we can build an ensemble that would just reduce the variance. And so we can see on the residuals correlation that ridge correlates with ARIMA pretty well, but then the other 2, the XGBoost and LSTM, are not really correlated. So from this square 4x4 here, I thought just take one from this group from the 2, and then just take this the other 2 and build an ensemble from the 3 models. And so that's what I did, and surprisingly it works significantly better than all of the parents, so to speak. Now the ensembling gives us more more improvement than for example multivariate, going from univariate to multivariate model. And so this is how it looks. And again, in some points, it sort of repeats the naive forecast, but not entirely. So this is a forecast, on its own, basically. I just tried quickly to understand, how the residuals look like, and they look okay. So they're pretty close to normal, and some unexplained artifacts here, like large deviations from the normal here and there, but generally, the residuals seem to be in good shape. And basically, the last thing I did is just visualize the performance for all the models, and we can see, how ensemble is significantly better than all of the other models. So that's very quickly what I did. I think my sort of conclusion from here is that basically there is very little information in the data. The data is very not fine-grained. It's coarse, it's rounded, and so my suspicion is whatever you do, it's highly questionable if this forecast can be improved significantly to, for example, 1 degree centigrade, etc. But yeah, please, if there are any questions, I'll be happy to answer.
Cool. Thank you, Dmitry. That was super useful.
So Dmitry, you did something that maybe you could elaborate on a little further to prevent the leakage from the last observation. Could you talk us through that a little bit more?
Yeah, so basically, it's a quick way to diagnose whether you have a leakage, because the worst leakage is the silent leakage, right? When it leaks but it doesn't tell you, it's not obvious that it leaks. Like you get some predictions, but whether they have leakage in them or not, that's the question. And so the trick to diagnose is to take the last time step that you have. And what I did, I just multiplied it by 1,000,000, and you train on the normal data, but at the during the inference time, you use that inflated array basically, and you make sure that your forecasts are not inflated. Basically, if you multiply like the last observation, the last temperature by 1,000,000, and you get 10 million degrees, and then your forecast should stay in 7, 8, 10 degrees range. It shouldn't be affected. So that's the quick way to diagnose, because if there is leakage, even if it's a like indirect or some sort of complicated leakage, when you distort the observations that much, it will be seen in the forecast. So it will be just immediately visible. So that's how you diagnose basically.
Sorry, Dmitry, my audio cut out briefly there. What did you say you multiplied to inflate it? What to get that?
So basically, I multiplied by 1,000,000, and the last row observations is just for convenience purposes only. But the logic is, if you're trying to predict the temperature for what is today, September 4, and you have all the data including September 4, and so you train your model and you multiply your September 4 temperature by a 1,000,000,
right?
And then when you run your forecast, you make sure that your forecasted temperature for September 4 is normal, is 10, 15 degrees centigrade, whatever. It's not million, because if there is leakage, you would see that it leaks into the forecast.
Right, gotcha. Thank you.
And ARIMA, ARIMA was tricky, because the stats model, ARIMA, is not a very sort of it's not bug free. It's a difficult package, and I spent quite some time making sure that it doesn't leak, and that's the only way I figured out it leaks, because I used that trick, and I saw crazy temperatures. So,
Dmitry, if you don't mind, if you have any resources later on, if you can post them on Slack, that'd be great, about this leakage approach, because it's new to many of us.
Sure. Yeah.
Awesome.
Okay, can I ask a question?
Yeah.
Yeah, it's about MAE. In the matrix, you have mentioned MAE. So do we have to make sure that it should be closer to 0?
I mean, ideally, the MAE is your error, so your objective is to minimize it. But as I said, first you have this bedrock MAE that you can't minimize, because the data is whole numbers, and your predictions are floating point. So you already there, you get something like on the order of quarter, like 0.25 MAE right there. So it's irreducible. But then, yeah, whatever you get, the lower the better MAE.
Okay. And another one is it's in the LSTM. Could you show that LSTM model?
Yeah. Well, what was the question?
Input shape. It's in the input shape. You have mentioned over there none comma as some value. So could you please elaborate on that?
So could you repeat the question, please?
It's a please could you show me that LSTM model? Where did you define that?
Here in the model itself?
Yeah, yeah, there you go. So my doubt is in the input shape. Could you please elaborate on that?
Yeah, so the input shape here, it doesn't include the batch size, right? So the LSTM takes the input tensor must be three-dimensional, so batch sizes, time steps, and features. And so time steps is your time dimension, and features is, you know, the width of your input tensor, like, you know, 9 variables we have here. And so, but in this, it's just a Keras artifact that you only mention 2 shapes here, and I could have had none. It's just I knew what the shape is, so I just put it here. But you don't include the batch dimension here, just the 2 time steps and the features.
Thanks a lot. I got it.
Cool.
Okay.
All right, Dmitry, if you don't mind making me host.
Yep.
And if you have any more questions for Dmitry in the meantime, feel free.
Okay.
So I'll go next, and then Robert, if you don't mind, you'll be going after me, and then David in the end. Just a slight change of order. Thank you. Thank you, Dmitry. That was a very detailed exploration. All right, share screen. Can you see my screen?
Yeah.
Awesome. Cool. So as Dmitry mentioned, I won't talk much about the pre-processing and all that. But my approach was a univariate approach. I did not try yet the multivariate. It's in my to-do list. And it's the ceiling that Dmitry mentioned of 1.5 MA that you're going to see consistently our models hitting it. And for comparison, I only tried deep neural networks. I didn't try any ARIMA or other models. I only tried one non-deep learning model you'll see in the end, and that's based on seasonality, and it's an additive model. So I'll be using TensorFlow here in Colab. I'll be importing the data from Kaggle. It's hosted on Kaggle.
George, can you increase your font just a little bit?
That would be my next question.
Sorry.
Is that better?
It's good for me. I don't know about others.
Okay. Catherine, good?
Yeah,
Cool.
that's good for me.
Cool. Awesome. So in Kaggle, you have an option to download what is called an API key, and it's a JSON file that basically allows you to interact with Kaggle, and so you can download the data. And once you upload that JSON file, you can specify some Kaggle commands, dataset download, and then the path of the data. And then you can extract it locally, and you can see it's just a CSV with all the features that you saw before. Some naming conventions here, as Dmitry mentioned, and this is exactly the same data frame. The only thing I changed, so we have about 7,000 records here. These are daily temperatures. The only thing that I changed was encoding the events original to categorical to integers. So instead of rain, snow, or nan, I just coded them as integers so I could work with them more easily. There's some basic data exploration, so just a distribution of mean temperature across the entire 1997 to 2015 range. And then maybe some simple correlation plots of how does average temperature and dew point, for example, correlate with each other. You can see there's a positive correlation here. So higher temperatures on the x-axis lead to higher dew point on the y-axis. So I did that for different ones. Humidity as well is negatively correlated. I didn't see much with pressure or visibility. Wind speed, there's a little bit. Again, this is, I think, better shown in Dmitry's charts where he did those factor comparisons. And this is precipitation. Cloud cover and wind degrees. This looks interesting to me. So then I'll scroll down. So yeah, exact same observation. Most of the, this is ignoring the NAs with the non-arithmetic numbers. So which I think is the largest portion in the events field. But after that, we have rain, rain, snow, fog, combination of different weather events. I wanted to see how the temperature looks like for different events. What is the average and what is the spread? You can see for fog, snow, it's below 0. You can see for rain has a wider distribution here. Now this is the average temperature. You can see some gaps here just by looking at the data, but checking for missing values again and checking for missing. I did not impute any missing values here like Dmitry did. I did not do that. So that was interesting to see from his approach. And for missing dates, we have about 127 or exactly 127 days. And here they are, 2000, 2004. So as a group, we decided to just keep the contiguous data set, which is basically from Feb 2004 till end of 2015. So from 7K records, dropping the previous records that had missing values, we have about 4,300 records. And then Seaborn has a nice pairwise visualization where you can see what is the correlation of all the features. I just thought to explore it on my own there. Then the next step would be to split our data into training, validation, and test. And we decided to keep 2012. So we have 2004 to 2015. The last 3 years, we're going to keep them as, for comparison, as a test data set. We're going to predict daily for the last 3 years, and we're going to compare it with the actual 3 years data. So after 2012, December 31st, basically 2013, 2014, 2015, that would be our test set. So anything up to 2012 would be our training set. Anything after that would be our test set. And for my own models, I also included a validation set of 2 years. So I have 2004 to 2010 training, 2010 to 2012 validation, 2012 to 2015 test. That was my how I broke it. Then when you work with time series, you need to construct your data appropriately. Again, if this is new to you, I highly encourage you to look at our time series video from the previous specialization that we took. It's recorded. It's on our first playlist on YouTube, where we go exactly row by row what does each one of them do. But basically what you're doing is you're trying to take the previous days or the previous day, and you're trying to predict the next day, and you assign features and targets there. And there's just a slight difference how you do that for regular deep neural networks and how you do that for recurrent neural networks. You have to expand the dimensions, as Dmitry mentioned, that none shape that you use in Keras for recurrent neural networks. Cool. These are some utility functions as well to plot results or multiple results if I want to compare different versions of my models. Okay. It's usually a good idea to clear your session in Colab and also set the seed for TensorFlow and NumPy. And we've seen that in the past, so I do that always for each model. So this would be my model version 1, and where we are right now. In terms of hyperparameters, I'm looking at 30 days of days, and I'm trying to predict the 31st day. And I'm taking batches of 32 sets, data sets together. And just to be more efficient in memory, Keras has this shuffle buffer size where you don't read all the data in memory at once, you read them 1,000 values at a time. So this is how I create the training set, the validation set, and the test set from this train, validation, and test series that we saw above. The first model that I tried was a simple DNN, dense, and then a linear output. The window size again is 30 days, and activation function is ReLU. I tried working with different optimizers, stochastic gradient descent. Didn't give me great results. I saw Adam gave me better. In terms of loss, I did not use mean absolute error. I used mean square error. And I was reporting on MA, mean absolute error. So 1,500 parameters. model checkpoint, a good idea to check the best model when you're training it. And early stopping if nothing changes for the last 10 epochs, you just stop training. And you're monitoring the validation loss here. So fitting the data, I just gave 100 epochs, but as you'll see after 57 epochs, there wasn't much improvement in the MSE, which is the loss function, or the MA. And I looked at from the 10th epoch and forward, just to ignore those high values in the loss function. Then what we're doing here is we're predicting on the test set, and overlaying them on top of each other might look like a great test. I think, Dmitry, you just looked at maybe a few days. Also, David, you mentioned that's a good idea to look at it, simply because of visualization might be misleading. So with that, I got about 1.6 MAE and 4.3 MSE. So I add that to my report. I also had the SGDs before. With SGD, I used to get much higher values. With Atom, I got 1.6, which is above that 1.5 threshold. Okay, in the interest of time, I'm just going to mention two more models. One of them is a more complicated one. It's based on convolution, 1D convolutions for time series, followed by an LSTM, followed by a DNN. So this one looks at 64 days at a time now. It has 32 parallel filters for 1D convolution. If 1D convolution is something new to you, we have another video again from our previous specialization. What does it do and how it operates? Followed by two LSTM layers and a DNN. Another interesting approach, I took some notes from our Sunspot notebook that we did in the specialization. I had to include here a lambda layer. A lambda layer is a custom layer in Keras where you can do any pre-processing or processing. For some reason, this model was giving me very low values, and I had to boost them up. I had to multiply them by a large number, and I played around, I think, with different values just to get the scale right. In other models, I completely removed that lambda, and they worked just fine. But for this one, for some reason, it needed it. Then the same compile with MSE, Atom, MAE. Now we have 60K parameters. Let's look at the visualizations. Again, it stops after 50-something epochs. About the same loss, maybe a little bit higher in the beginning. So version 2 is the orange one. And MAE, we dropped to 1.54. So we did a little bit better with this way more complex model from 1.61, 1.54. Then I tried something simpler. I heard David, why do you even need convolution 1D? Just use LSTMs. So I took his approach, just LSTMs. And I think this was my best model, 50,000 parameters. Green is the version 3. As you can see, trained it for even more epochs than the other two. Overlay 1.50, and that was like a ceiling for me. Like, why am I not able to reach this 1.50? Cool. Then version 4 is something that was interesting. If you notice the temperature here, the range is from negative something or 0 something to 30 degrees Celsius. Maybe it's a good idea to scale this to maybe from 0 to 1 or negative 1 to 1. That's very useful in deep learning. So then my next adventure was, okay, let's see if we can normalize or standardize the input. And I have a link here, but basically if your data is normally distributed, then it's a good idea to standardize them, meaning you subtract the mean and divide by the standard deviation of your training set. Make sure you do this make sure you extract the mean and standard deviation from the training set so you don't have any data leakage. And if this is not true, then you could do something which is called normalization, where you look at the range, the minimum and the maximum value of your times of your training set, and you scale everything in your training set, validation set, and test set to be between that min and max range. So I did normalize. So I did basically trying to stay between the min and max. This is not a good idea if you have an upward trend, like Dmitry mentioned. Do you have a slightly upward trend? So this maybe might not be the best approach. But given that it was so small, I went with this min-max approach. And I normalized the training, just to give you an idea, this is the training set before, after normalized, and you can also inverse it so that you can compare it against the real test set. So this is the training distribution. This, you can see it goes from 0 to 30, and this is the normalized. It goes now between 0 and 1 because you have that min-max range. Standardized, -2 to 2, average around 0, just to visualize. Okay. Then I tried the exact same models, the DNN and the LSTMs. I noticed when I use normalization, I should not use batch normalization. It actually makes my performance worse as well as dropout. So one of my observations in the end is that when you do normalization, don't do batch normalization or dropout. And with this model, let's see, got so if you compare the actual values, the normalized values, you're going to get a way smaller MA simply because the values are much smaller. You have to inverse the operation that you did on the output, and when I do that, I get about 1.57. So I didn't really improve much. Again, this is the running list, 1.57. Then 5, I tried another one. So that was a DNN. I tried a Con1D. I tried a 3-layer DNN. Not to bore you, just quickly go to the results. But basically, with normalization, I didn't really gain much. I tried another approach from scikit-learn. I'm not sure what I'm doing wrong here, but I'm getting way worse results. And the last model that I want to talk about is a non-deep learning one. It's called Profit. It's from Facebook's data science team, and it's based on it's an additive model. It combines seasonality trends. It even has the ability to combine special events. So if you know you have holidays, or if you know you have, let's say this is like a game and you're trying to predict attendance, you know, when the days that the game is happening, or when Christmas is happening, or maybe when traffic is happening, like you mentioned, Kathleen, you can include them in your model. You need 2 packages to install this, and I tried the univariate approach. It just needs 2 labels, the timestamp and the target, and you fit it like this. It follows the scikit-learn dialogue, the way and look and feel, and you can do future predictions, how many days you want. I did the last 3 days, and then it gives you, by default, it gives you so many other parameters. It gives you upper and lower bounds, trends, weekly trends, annual trends, daily trends, and the y-hat, which is what we're interested in. So in dark blue, in blue and in black is the actual, so in black is actual time, our actual data set. In blue is the predicted value, and in light blue is the upper and lower bound for that predicted value. And you can also break down your model in terms of trend. What is the trend of the temperature? As you can see, it increased a little bit in 2006, it increased in 2008, it increased in 2012. What is the weekly trend? So if you look at all these different years, usually Wednesdays, Thursdays, and Fridays for some reason and Saturdays are warmer than the other days. And in terms of days, as you know, weather is seasonal, so June, July, August, September are the warmest months. So then when we did the prediction right here, let's see how it scored. It did a very smooth prediction here for my last 3 years. And it actually scored 2.4 MA, which is not that great compared to other models. So again, this is the Profit one. So this is my approach based on univariate time series. I had the MSC as well, and some observations and key takeaways. Some hyperparameter tuning. SGD didn't help. Early stopping for me usually happened around 50 epochs. Usually stable network helped, but not always. Normalizing the inputs didn't really help me. Usually it helps. For me, in this case, I don't know. It didn't give me much gains, actually make it slightly worse. And If I'm normalizing, I need to make sure that I'm not using batch norm or dropouts. When plotting normalized values, make sure that they're in the same range. And if you want to compare against the X test or the test data set, you need to inverse that scaling operation that you did. And that's the 1.5 ME that Dmitry mentioned, that naive forecast. So my next thing would be to consider multivariate, where you're considering multiple features. And the other thing I'd love to try is maybe if I can predict this events field, basically if it's rainy snow, rainy fog, windy, based on all the other features. So basically do some kind of classification of future weather events. That was my approach. Any questions for me?
I was curious. Thanks, George. That was good. I was in Dmitry's presentation. He did a bunch of models like you did, and then he correlated them to see which ones did not correlate, and then he created an ensemble from the uncorrelated. Is that something that you could? It looks like you could have done that here, and I'm just, is that something that sounds like something reasonable?
Yeah, that's maybe something I can add to it, but I could see more gain, as you saw in Dmitry's approach, of exploring more features than just sticking with the temperature one. That way we can break that 1.5 MAU barrier here. We could go even lower. But yeah, if you did an ensemble, I doubt you'd break still that.
Well, yeah, I know. I probably should ask Dmitry this, but I was more interested in like the approach to, pluck out of the, which ones you might use in an ensemble and which ones you would discard. So it's when you do such a correlation, is that you're just correlating the results somehow of the temperature results. I guess I'm trying to figure out what correlated there. And then maybe you don't know. That's okay. I should ask Dmitry.
It looks like he was doing some kind of residual correlation. He was looking at what was the predicted value minus the true value, and he was seeing how those residuals correlated for different models. But
yeah, exactly. Yes.
Okay.
Yeah. So, but actually, the way I did was not very clean and scientific, because I correlated the y-hats, the predictions on the test set, which I shouldn't have done. So you correlate on the, validation, and then, you see which ones are not correlated, and then you build, your ensemble model.
Okay, thanks.
cool. Awesome. Okay. Any more questions
Hey,
before we get
yeah,
Robert?
George, I was wondering, Dmitry mentioned about the sort of linear trend in temperature rising over time. So I was wondering, given that it's not a huge increase, with the way that you've done your train test val split in those time segments, do you think that a gradual increase of temperature affects, if you're training on earlier stuff and predicting for future stuff, that it's going to pick up on that trend, or do you think it's insignificant enough to not make a difference?
Yeah, that's a good question. I think if you have a significant trend, yeah. One thing that we've seen in other models, in other coding challenges, is that deep learning models are not good at extrapolating, meaning if there's a value that I haven't seen yet, they won't be able to produce or generalize it. So if there's a trend and you only train for the last, in the past, let's say the middle of it, but then you're trying to predict in the future, I think you'd have issues. You wouldn't be as accurate.
Right. Is it, would it be valid to take a more, I know this is sort of weird for time series, but to take a more random train test split and predict rather than doing it in segments?
That's another approach. I don't know if it's popular in time series. Like you're saying, pick random samples for training, random samples for validation, random samples for testing, but then you
right.
kind of lose the sequence part of it.
Right, yeah.
That August 2012 is actually after August 2011. So I don't know.
Right.
Because time is there. If this was not time dependent, for sure this that would be the right approach to separate your data. But I don't know, does anybody know if this is time series? Can you do random sampling of training validation tests instead of non-overlapping? Like,
Yeah, I've seen
sessions.
Once I followed one approach, like she's saying that you can randomly split your data. So in that case, we might need an index in our data frame. So once our training is done, then we can reconfigure our data into the same time series. So there's some kind that index won't be a part of the training data set, but just to recover the last data. It gave
Right.
me good results at that time, so this approach can follow one.
I'd say it kind of depends on what your task is as to whether it's a reasonable approach. Right? If you're doing forensic analysis, then it's kind of fair to consider all the data. If you're trying to assess how well you might be able to predict in the future, then it's not really the same thing if you're looking at splitting data randomly.
Do you know how to incorporate in a time series model like this a linear trend like that? Is there a way to sort of build that into the model, that it is acknowledging an upwards trend?
So I was going to do that. I decided not to, but you'll see a little bit of that approach of how you would do it anyway, or at least how I would do it.
Cool.
The other way is, instead of adding that feature, you remove that feature. So you pre-process your data to remove that linear trend.
Right. Right.
Cool.
That means that you already know the trend and you can add it back into your predictions at the end, right?
Yeah.
Right. Right.
Sort of like you're taking out a constant factor. If the trend has any variation to it, like, you know, global warming seems to be exponential, it's a hard trend. You've got to predict that trend too. You can't just subtract it out, right?
You can even remove seasonality if you want and then train on that. But then you have
right. Right. Now I will maybe throw out the fact that once you have created your windows in a time series, you can shuffle it all you want during your training. That's what's actually happening. TensorFlow behind the scenes is shuffling these batches all the time, right? So you're not training in any kind of, you know, your batches of your windows are not in series when it's training. You could do the same thing when you're running your test. You could have shuffled your test data. I don't know why you would, but after you create the windows, not before. But if you were able to, you know, create your windows beforehand, you could feed them in any way you want, because that's how it's, right? Does that make sense? So,
right.
But yeah, you definitely can't do it before you create your windows. It's
right.
And then you train on shuffled input of training validation tests. Yeah,
right.
Yeah, that makes sense. That makes sense.
Okay.
And George, I was also wondering about when you added the batch normalization and dropout. Was that just experimenting to see what effect that had, or did you notice something that you wanted to? Was there a reason why you added those in?
Yeah, that was the easiest way for me to introduce some kind of normalization on the network. So I tried batch normalization and dropout. It didn't help me much. It actually hurt my model when I had normalized inputs and batch normalization. So for sure, I knew that something was wrong there. So I can either do one or the other. And I noticed with normalizing the inputs, it's slightly better than just doing batch norm. All right, Robert, if you don't mind sharing your screen. Sorry, there are some questions on the chat. We're trying to get to them. If you don't get to them, we'll follow up on Slack. Thank you. You're muted.
Let me share my active window rather than. I think this is the one I intend to share. Let's try that. Can you see my screen, the Jupyter Notebook Madrid weather?
Yes, yes.
And you see me scrolling it? Okay, wonderful. So I took a completely different approach to this. A lot of EDA and some very simple models, but hopefully we'll learn different things from each of our approaches. So this notebook is far less polished than the ones you've seen already, but I hope that it's just a different way of looking at this problem. So as the others did, I began with some exploration. Dmitry was kind enough to share his code early and had some helper functions in it that I cannibalized. So I renamed all the variables as he did, and I also borrowed his plot series routine as well. So thank you for that. Just a few, I mean, people have already gone over a lot of the exploratory analysis so far. I'd say a couple things that I did that are a little bit different are I added a field called DOY, day of year, and actually expressed it as a fraction. So that is basically it's 0 on January 1st and it's 1 on December 31st. And added it to the year. This was in part of my trend investigation. And let's see what else. Just a bunch of pre-processing, described step. Here's the plot series. I not only borrowed it, but also modified it a fair amount to handle a few extra cases. Made it a lot less pretty looking, but a little bit more general.
Robert, are you going to explain why you did that DOY thing?
I think so I wanted to use that to help build a seasonality model. And I will go into that later.
Okay.
For right now, it's just another predictor, which is, you know, between 0.0 and about 0.08 during the month of January, becomes about 0.5 by the midsummer, and goes back to and reaches 1 at the turn to the next year. So I plotted the, this is just a scatter plot of the temperature against the date. And one thing that I found, which was kind of weird, is this phenomenon that there aren't very many points here at certain temperature values. So if you look at this, this plot here, I actually colored them a different color. But if the temperature was divisible by 5 and not by 10, there was far fewer data points on that particular temperature value. I thought, you know, maybe it's a measurement thing, but the measurement process didn't really change. The only thing I did notice is that this phenomenon does not occur in the max temperature or in the mean min temperature. So I believe this is calculated and binned somehow in some odd way that reduced the frequency of those measurements. But I just thought it was a rather bizarre observation about the data set.
Very.
You know, you've got 20 or 30 points in the entire data set with these values, with each of those values, and you've got 200 and some at the other nearby integers. So I couldn't explain it, but just thought it was interesting.
Would you have noticed it if you didn't plot the data in that particular way where it kind of showed this band going across?
Well, I noticed it when I plotted the data this way.
Yeah, still kind of there. Yeah.
And it's still kind of there, and then I just emphasized it in the next plot.
That's interesting. Huh.
So other basic observations that I had at the very beginning of the task, kind of the obvious ones that people have already talked about. First of all, there's clearly a seasonality here. We've got to figure that out somehow. There might be a trend. We've got to figure that out somehow. And there's also some missing data, so we need to figure out what to do about that. Now, it's not so evident on this plot, but there's kind of a hole here in early 2000s. And there's a couple of other smaller holes. I'll show a little bit more about that later. So these were the value counts that I just skipped and showed, and these are the mean temperature, which is the blue line that we already saw. And just to show that that phenomenon did not occur in the max and min temperatures, we've got the orange and green series here. So the next thing I did was, just kind of highlight that on another separate plot here. But in particular, I was thinking, well, maybe the mean temperature is computed somehow directly from the max and the min temperature. So this is essentially looking at the average of the max and the min. It's really just the sum of the two, not divided by 2. And against the mean. And it does seem a little odd that most of these values correspond to 3 or 4 different values in this sum, but these ones on the 5s don't. Again, just kind of bizarre. I didn't end up acting on that at all beyond that. So now we get to missing data. And if we look more closely at the data set, the missing data that occurs in a data set that is between 1997 and 2015, the missing data all occurs in a 4-year span between 2000 and 2004. And if we look at this particular plot, all I've done is taken the 4 years worth of data and plotted it in blue. And the orange lines here signify where data is missing. So right here in 2000, we've got almost 2.5, 3 months that are missing. And that's why you see this line just kind of connecting one point in February to another point in May. The other missing blocks are much smaller. There's a handful of points missing here, maybe 1 point, maybe just 1 point or so missing there. And then in early 2004, there's another month that's missing. Just a closer look at the earliest part of that time series. So the question is, what do we do about the missing data? And there are a couple different approaches. I will say that the easiest approach is to do what all of us have done and pretty much discard all the data starting before 2004 because the last 11 years are all contiguous. So we split off a 3-year test set and you still have 8 years to work with before that are completely contiguous. So one question that I wanted to look at, but did not actually do, was, could we possibly improve our models by including the earliest data? I suspect it won't help much because I just don't think that the weather patterns vary enough across years that early data is really going to be helpful for model generalization. I think you'll probably learn enough about typical weather patterns in 8 years worth of data that the early data won't really help you avoid overfitting much. So, or improve your models that much. That's just a guess though, haven't tried it. So I did what I believe everyone else did, which is just to start at 2004, February 1st. And from that point on, the data are completely contiguous. So another thing I did was looked at offsets. So the idea being that we're interested in seeing how the temperature changes from one day to another. What is the distribution of the differences as a function of the number of days offset? So for instance, if we know that yesterday was much warmer than average, it's probably going to be somewhat warmer than average today. And so we would expect the long-term averages to have less of a tight distribution. We expect, when we have offset equals 1, it should be a kind of a tighter bound. And if offset is larger, it's a larger, more representative of the entire season's distribution. So in this case, we do see that the offset of 1 is peaked around a 0. But what's interesting here is that really, if you go beyond more than about 3 days, you don't really find that there's that much correlation beyond the season itself. So for instance, I chose 365 as one of my offsets just to compare it to the data from the exact same date the previous year. And that's the purple line here. And the green and red lines are really no better than the purple line. The orange line here at offset 3 is maybe a little bit. One thing you have to worry about when you have offsets like 14 is that now you're starting to develop some kind of a systematic bias, right? If you know that your day is in October, then you might expect the day 14 days later, just on average, to be cooler because the season's changing. So this was just looking at the standard deviations of each of those distributions and looking to see now expressing this as a function entirely of the number of days offset. And we see that that standard deviation does really start to flatten out as you get above about 5 or so. And this is the same, but it's with the mean of the absolute value instead of the standard deviation. So the approach that I took as far as trying to fit the models was, first of all, see if there's a trend. Secondly, design a seasonal model to try to fit the seasonality in the data, and then look at the residuals left over from that and fit a predictive model to that. So I looked to see, okay, is there a trend? I took a somewhat different approach and got a somewhat different result to that question than the others. So I'm curious to actually see what the differences are in that. So what I did was I didn't want to bias the data by including some of the missing measurements without the ones that weren't missing. So for instance, the year 2000 had a bunch of measurements in March and April that were missing. 2004 had a bunch of measurements in the winter that were missing. I basically said if there was any time at all in the calendar year that there was a missing value, don't use it and just look at this plot here. Just for visualization purposes, not for model fitting. And it looks like 1997 might have been a particularly warm year, but otherwise there's maybe a slight trend upward. I tried to fit a model to the years themselves, and it actually turns out to be negative using a mean squared error loss. It seems like maybe this one point here was enough to move it into a very, very small negative value, just barely less than 0. Not significant at all. But in any case, it seemed like if there is a trend, it might be almost negligible, so let's ignore it. So seasonality, this was an interesting one. We know that the period should be a year, and now we're going to get into why I did this whole day of year thing. So we're converting January 1st, 1997 into a very small decimal and converting the last day of the year into a 1. And now what I want to do is essentially build a Fourier series to convert these numbers into a linear model. So I take sines and cosines at a variety of different frequencies. And just to show what that looks like, we have the sine at the smallest frequency is small numbers that are increasing. Cosine starts at 1 and is decreasing. Sine at double the frequency just goes up twice as much. And these are just basically Fourier components. And what I'm going to do is build linear models based on these Fourier components. So just looking to make just gut check to see if we did it right. I fit 10 different seasonal models, each of which went up to a different one of these components. So I fit one model that only used the I guess if I point at my screen, I should probably do it with the mouse. Sine 01 and cosine 01 I used for one of the models, and then this, as well as a constant term. So that's 3 parameters. And then I fit another model that used up to sine 02 and cosine 02. So that's 5 parameters here. And fit a third model that had 7 parameters and so on. And these are all linear ordinary least squares models that I fit using stats models. And looking at the results here, not terribly surprising that in the first order model, the sine and cosine coefficients are extremely significant. So statistically, it's extremely statistically significant. So what I wanted to do was, let's see, I think somewhere down here, yeah, here we go. We have the orange line is the seasonality with a first order model and seeing how it mirrors to the temperature. So it does a decent job of capturing that behavior with just a perfect sine wave. Somewhere in this notebook, I compute the amplitude and phase fraction, phase day of that first model. And right here, the amplitude is roughly 10 degrees. So it's about 10 degrees warmer in the summer than it is on the year average, and 10 degrees cooler in the winter than the year average. And phase day, this basically told me, confirmed that the winter trough in the data is occurring around January 21st, which is reasonable and suggests that it's done correctly. This is just zoomed in on the same thing. So I thought it would be interesting to look at, okay, take the residuals after subtracting out that seasonality. There's a whole lot of structure in this plot due to the discreteness of the target variable. However, it doesn't look like there's a huge problem as far as difference in the distribution of the residuals as you move across the year. This plot is not labeled, but the bottom is this day of year fraction. So we're looking at January here, summertime in the middle, wintertime over here. And these are the residuals based on the seasonal model alone.
Robert, the x-axis, is that the 1 year or all the entire years of the?
This is every year. So I've just taken every point in the data set, assigned it its day of year relative to basically giving it a phase angle in the year space, and plotted it accordingly.
Each time period is a year then? Is it a different year?
Excuse me?
Each blue wave, it's a different year?
No, each of those blue waves is actually just a different one of the discrete values in our target variable temperature bins. So actually, if you look at this one band here that has very few points, that corresponds to 15 degrees, where we had very few points in our data set. And this is 25 up here, and 5 is down here. And this is just kind of showing how what we've done is we've subtracted the sine wave from the data, and by subtracting it, it makes the original data give it these sine waves into it.
What would axis X and Y be here in this example?
Yeah, so I didn't label that for some reason, but these are the X is the day of the year expressed as a fraction of the way throughout the year. So 0 is January 1st, 1 is the end of December, 5 is the near the summer solstice, and the y-axis is the residuals.
I see. Okay, thank you.
And so looking at the training set, well, okay, what I should actually do is skip down. I fit this once using all the data, and then decided, well, if I want to pick a model, I need to choose a validation set and run on that separately. So I split it into a train and a val set, fit these 10 same models again, got very similar results on the training set. Here's the RMSE. So obviously in the training set, you would expect that the more parameters you give a model, the better it's going to do, because generalization doesn't matter in the training set. But when you run it on the validation set, which was the last 3, I believe I just, chopped off the last 3 years of the original training set. So on the validation set, it's a different story. Here, the second order model is actually the best performing one. The other ones start to show that you're probably overfitting as soon as you get a model of order 3 or more. So I decided to just model the seasonal variation then with a Fourier series of only first and second order sine and cosine terms.
Is RMSE somehow related to MAE, or are they just completely different metrics? Robert?
RMSE is just it's the square root of the mean squared error, and the MAE is the mean of the absolute value. Don't think I showed the MAE here, although I do later down.
Oh, perfect.
So at this point now, we assume if we take this seasonal model, subtract it off the data, now we should be left with a model that doesn't have seasonality, and we still have an autoregressive behavior in the model. So we need to try to build an autoregressive model on the residuals. So I thought, well, maybe AR1 considering just the day before, AR2 considering 1 and 2 days before, AR3 considering up to 3 days before, just remembering that plot that I showed earlier where it didn't look like it was that useful to know beyond 3 days previous in order to predict the next day's temperature. So I thought, well, let's just narrow it down, only think about those models. Defined a helper function here for plotting time series. Also chose clean selection just to cut off the part of the data that had missing values in the front. This helper function does some time series analysis on the data. In particular, it gives a plot of these residuals. And this definitely looks like an autoregressive type model where you have not white noise, but definitely noise where residuals of the same sign are all kind of near each other. And this helper function also plots autocorrelation. The autocorrelation is, of course, 1 at 0 offset. It drops to a little under 0.8 for a lag of 1 day. And because autocorrelation is an infinite impulse response, it just kind of slowly declines from there. And in fact, a useful way to think about this is to compute what they call partial autocorrelation, which is to remove the known effects due to the first order autocorrelation. What is the residual effects due to the next previous predictor? And in fact, when you look at the partial autocorrelations here, you find that as soon as you get beyond 1 day, you don't really learn anything by looking any further back in the history. So with this seasonal model, all you really need to do is look back 1 day. So you have your seasonal model to tell you what time of year it is and what you should expect, and then you know what the previous day's temperature was, and that's it. So as I say here, this is strong evidence for AR1 being a sufficient model for this set of residuals. This is just a scatter plot of those residuals. I'll jump forward. I actually just did this by hand, an ordinary linear least squares using the same stats models. There's a REMA within stats models package as well. But when you're doing an AR1 model, it's really just a linear function of a single predictor. So I'll just kind of run through this. This was, as I said, it's not polished and it's not very easy to follow. But what we found in the training set is that the standard deviation is very low, and the MAE here is ridiculously low on the training. But that's just the training set. So let's move forward onto the validation set. Final predictions on the validation set, run the same process. And MAE is right about 1.5. So then I just took the same process, applied it to the test set. Had to do a number of computations because I hadn't prepared some of this, some of these sine waves in advance. But the end computation on the test set is, first of all, compute a seasonality. So you have one constant value plus 4 sinusoidal coefficients multiplied on the year phase, and then plus another coefficient autoregressing on the most recent value in the time series, and another constant here from the autoregression model. So overall, really, this is a 6-parameter model when you think about it. Just 4 parameters here for the sinusoids, 1 for the autoregressor, and the 2 constants could be absorbed into 1 constant. It's all just a constant. Test predictions, computed test residuals, and test MAE is very close to validation MAE. Get about 1.48. So I think I kind of raced through this, and I raced through it myself as well. So there's definitely some, it hasn't been as cleanly polished or configuration control. So certainly should be a second look taken at it. But it's just a completely different approach, using far fewer predictors for a univariate time series. Sometimes that's all you need.
Awesome. Thank you, Robert. This was very interesting. I was kind of lost, to be honest, while you were going through this, but I'll go through your notebook and hopefully I can catch up. But
well, my notebook wasn't designed well for presentation. It's still a work in progress.
Doesn't matter. I love that you broke that 1.5 MAE wall.
Well, yeah, barely.
Cool. Any questions for Robert? Getting a bunch of thanks on the chat, by the way.
Do you feel like it was basically learning to predict today's weather from yesterday's weather, kind of like we were seeing with a lot of the other models, or do you think it was actually doing more than that?
I'm sorry, can you repeat your question?
So a lot of when we looked at the plots of the predictions, basically it was learning that naive, predict today's weather from today's temperature from yesterday's temperature. Do you think it's doing something similar? Because you said it's using one day, seems to be really important, right?
Well, it's using one day after having learned
seasonality, right? Yeah.
Learning the seasonality, I didn't go into it too much, but the RMSE of the entire data set is around 7.5 if you ignore the time series aspect of it at all and just consider it a single set. The standard deviation of the entire set of measurements of temperatures is 7.5.
Okay.
The seasonal model reduces that to a little under 3. So the seasonal model right there is explaining about 60% of your variance.
Yeah.
And then the autoregression helps you get up to about 80%, where you get to 1.5. But I thought it was really interesting that once you had that information about the seasonality, you really didn't need any more information about the current weather other than the previous day's temperature.
Right.
Got it.
Interesting to
What was the temperature 365 days ago, and what was the temperature 1 day ago? That's all you need?
No, you've trained an entire model based on seasonality. So you're not looking at just the temperature 365 days ago. You're looking at, based on 8 years of data, what is the mean temperature expected on this calendar day.
Got it.
Which is very different from looking at one measurement.
Yeah.
Like not only are you looking at 8 years, so it's not just even 8 measurements either, because you've fit an entire sine wave to it. So the surrounding days are playing into that fit as well.
So back to your original questions, were you considering of using the entire data set with the missing values you think would help a little bit with seasonality or prediction? Right,
Well, I came to the conclusion that I didn't think it would help much.
Cool.
But that's just a hand wave guess at this point.
Cool. Any more questions for Robert before we move to David?
I had a question. I've seen the Fourier transform being used on sound wave patterns as well. What exactly is the Fourier transform doing for as far as trying to get the, I guess, make the data more readable, or trying to get the information out of it?
I'm not sure I understand the question. The Fourier transform is just being used to try to learn as much as possible about seasonal weather patterns with as few parameters as possible.
Gotcha. So is it kind of like principal component analysis then?
Sort of. From Fourier theory, you know that any periodic function can be represented as a sum of sine waves of various frequencies, where the fundamental frequency is essentially where I used a 1 there. Well, actually, I think there is a fundamental component that that I ignored. I was only taking the fundamental might be, you know, if the no, never mind. I'm misspeaking. I was using fundamental as 1. But as you try to approximate a function, you may need more and more of those components in order to match the function. One important thing about Fourier analysis that I did not mention is that it works pretty well for very smooth functions. And where it has difficulties is approximating functions with a lot of discontinuities or sharp changes. Because you're trying to approximate a function with sharp, jagged edges in it by only using a bunch of smooth functions. But in this case, I expected the weather seasonality model should be pretty smooth, and I didn't think that it was going to need a whole lot of parameters. I was actually surprised that the validation set ended up telling me to use just 2 orders on the seasonal model.
Gotcha. Thank you.
Mm-hmm.
Cool. Thank you, Robert. Do you mind making David as a host? Just click on his icon.
Sure, I will do that.
Awesome. So we've seen statistics, we've seen machine learning, we've seen deep learning. This is awesome.
We've seen all the way from what, 50,000 parameters to yeah.
That was the most efficient model. I love it.
All right. So I'm not going to go into my notebook too much. Feel free to go through it. I posted it. It's very similar to what everybody else has done and shown. A couple of things I will point out that I looked at. First of all, there's a link here to what's called MetNet, which is a deep learning model. It's from Google, and it's not forecasting on this type of data, but it's forecasting with deep models, and it's beating every physics-based model out there, which I thought was interesting. It's the best, most accurate we've ever seen. So it's very interesting. I expected we would see the machine learning approaches, the statistical approaches here beat our deep neural networks by a lot. So I put this link in there just to say, hey, wait, we can do better. Anyway.
I presume that's using multivariate data with a lot of features?
Adds a lot of features. It's even got imagery in there. So yeah, it's set up to be good for.
Click on it, it's like Alice in Wonderland.
Yeah, but it's very interesting to see their approach. It's kind of, so I just put that link there. So the first thing I was going to look at, I did several models like everybody else. I did a baseline, which people might be interested in. It's the naive model of, choose today's weather based on yesterday's weather. But I just wanted to show how I did it in TensorFlow with just a simple, my input's coming in, that's standard input that we're all using. But then the output is just a lambda function where I use the prior day's weather temperature as the output. So it's very simple. No need to do any training on this since it doesn't actually have any parameters that are trainable, and you'll get the typical. This is, I will point out, if you see my my MSEs and my mean absolute errors, these are my my scaled ones. I'll show the unscaled ones at the end, and they're very similar to what everybody else saw.
How you hack TensorFlow to have 0 training parameters?
Yeah, well, I mean, it didn't use them, right? It's lambda's just saying I'm going to spit out the thing back to the last value.
You need to compile just for syntax, I guess. You need Atom just for syntax.
I think in order to actually get a summary, you'll have to either build or compile your model. I don't know if you can do like things like evaluate and predict, which I'll do down here without doing compiling. Probably the optimizer doesn't matter since you're not doing any training.
Yeah.
This compile sets it up for training. So you're right, you may be able to get away with not even doing that part. I didn't try that.
I would assume that you would only need to specify an optimizer loss or metrics if there aren't defaults already for those things.
Yes, right. I'm not sure the optimizer, since it's only for training. Your metrics may be important for when you're doing evaluation and predicting, but I don't know. So the next model I tried was a deep neural network. It's not very complicated. I put dropout in there because it was overfitting. It's a very simple model. It's very similar to what George showed. And then I did 3 recurrent neural networks, a simple RNN, where I didn't really spend much time on this. It was more just proof of concept. A GRU model, which is different, another type of a recurrent neural network. And then my LSTM model. And I spent some effort on this one to try to get it to get me the best value. It's about 1.2 million parameters. And the last thing I did was, these were all
hey, David, are you picking ELU because you found that it works better for you, or is it just kind of?
In this case, I didn't see much change. I don't know if you saw, like, I've tried several different ones, but I didn't.
It is just your experience that it's better than ReLU, say, or you just?
It can be. It can be for certain problems, yeah.
Okay.
There's also a newer one called Swish.
Yeah, I was about to ask, what was that?
Yeah, that's a newer one. I'll let you look those up. It's a long talk to explain the differences, but basically, no problem. See the functions. If you look at the plots, like there's some good places online where they have the plots of the different functions, and you can kind of see what they are. We probably should have a series of going through the different activation functions. Again, that was probably just the last one that I put in there, but I didn't see a lot of difference between them for this particular problem. And then the last thing, those were all univariate attempts, and here I just wanted to play around with some of the multivariate. So I only used the events. I put events in there just for fun to see what the effect it would have on this. So I'm gonna show that. The one thing I did was I didn't want to. So if you do like a labeling coding or just basically convert them to integers that are in a sequence or whatever, then you may be saying that the order, that 1 is different than 12 because, 1 is lower or 12 is higher, so you're giving some importance. So I just one hot encoded them, and that gave me a bunch of additional features, each, as a 0 or a 1. So, was there rain, was there not rain? Probably didn't make any difference because it didn't help much, but there with this model, I used the LSTM model again, but here in the input shape, now I have, instead of just the temperature, I've got the other 13 events also included. And I wanted to get to show you the results. Let me look at the DNN real quick. There was one thing, there was a question earlier about it. Here I wanted to point out, this is the predictions against the test data, right? And here you can clearly see that, it basically got really good, as I think Dmitry pointed out. It's very good at learning the naive model. When we zoom in, we see it's basically replicating the naive model very well, which a lot of these networks are doing. But the other thing I want to point out, it also doesn't extrapolate up to these new higher temperatures that it's never seen before. So the trend, is going much higher, and it's not able to extrapolate up there. So I thought that was interesting that that was showing up.
Yeah, that happened to me too, David, by the way.
You saw that as well? Okay.
Yeah.
So yeah, not only was it learning the naive model, it couldn't even do it for the...
but at extreme temperatures, it was bad.
Yeah. And then here's just a printout of the report of the summary. For the baseline, naive model is 1.47. Some of the other RNNs are getting very good at learning that. This is, I think the last time I ran here, this is for 60-day window. The DNN didn't do as well as the others. I thought it was interesting that the MSE is going down though. It's actually improving quite a lot. And maybe Robert can comment on that in a little bit, or now if he wants to. But we weren't able to improve the MAE, but the MSE is definitely going down.
That's weird.
So then the other thing I did different that I didn't see anybody else do was I gave a bunch of different window sizes. And my hope was that since I wasn't building any feature like Robert did to build in seasonality, although I have seen people use the signs and things actually with some of these deep learning models also to build in seasonality as a feature. And I want to do that eventually. But so what I did was I thought, well, maybe if I give it a much bigger window, I can begin to capture some of that seasonality in the models. So I started out with the 30-day window. You can see my LSTM is basically learning the naive model, and you'll see that repeated throughout. Then I went to 60 days, not a lot of change. And then here I'm showing a whole year, and there's a slight variation in this because of my my normalization is going to change based on the window. So that that's going to change a lot, but it doesn't change much. It's that 1.5 that George likes. My LSTM actually beat it slightly here. So I don't know if it really did learn something. And then I gave 2 years. So on the 2-year window, I actually could not do better on any of these. Although my events went below, adding in the multivariate seemed to be making a difference here. But what I thought was interesting was the deep neural network continually gets worse as I increase the window size, which did surprise me a little bit. And then I think in the future, things I wanted to try was more of the multivariate features, adding those in. I was going to use some regularization on the DNN model to see if it was, because I was seeing some overfitting there that maybe that might help with. I don't know if maybe an attention layer might capture some seasonality or something. Probably not, but something to try. And then for fun, I wanted to try to, George had mentioned this, try to predict the events based on the other inputs. It would be a fun activity. One of the things I wanted people maybe to comment on was the fact that we train on, you know, like the first 6 years or whatever it is, 7 years maybe, and then our validations on the 3 years, and then we're trying to predict, you know, 3 years out from that. And so I thought that was interesting. There's a big gap there. The reason I needed validation in my models is so that I could not overfit, so I know when for the model to stop. And I thought, well, if I didn't need that, then I could train on the whole data up until when I want to predict. And I wonder if we'd see better results if we could figure that out.
Well, would you not, after fitting a model and deciding based on the validation set, would you not be able to just train on the whole train plus validation set with that?
Yeah, so I've seen people do that. The thing is, you maybe have to like take a guess as to when to stop the training so that you don't overfit. So the idea of the reason we were looking at like early stopping with monitoring our accuracy on the validation set was we could kind of tell when we were starting to overfit, right? Or we're also looking at when we're no longer improving. But for me, it was necessary to have it so I didn't overfit.
I guess that makes sense.
So I'm not sure if you could reduce maybe your learning rate or something to keep it from overfitting and then train on the whole thing.
David, did you try MAE as your loss function in TensorFlow?
No, I used MSE for all my models.
Okay.
That's our next thing to do, try MAE, Dmitry, based on what you did. But regarding your question, David, so you're saying you have a training, a validation, and test. First train your model on training and validate it on the validation set, then consume the entire training validation into one training set. Instead of doing that, can you maybe do chunks? You do training validation, then continue to make that validation set smaller and smaller and smaller and consume it slowly.
Yeah, and there's that. You could do like a cross-validation.
Yeah, that would be more data, and you also have that early stopping, so you know how you're doing. But at some point, though, you have so less validation data.
Or you're actually getting a good measure of how well you're doing. If your validation set gets too small.
Mm-hmm. My other question is, did all your models include normalization or scaled inputs? Is that the case?
Yeah, I use normalization for all of them.
Can you show us real quick? How did you do
that? So I did more of the manual. You could use something like scalar standard scaling or something, but I choose to use the, let me see, I think it's up here. Is this where I normalize? Yeah, so I'm just subtracting out the mean from training and dividing by the standard deviation of the training set.
So you did
for all three.
Yeah, perfect. And they were all univariate except for the last one, which was multivariate that had events as an extra input.
Yes, yes. Mm-hmm. And I proved, basically the same thing that Dmitry basically showed, that the events were not that important. They didn't help me at all. So.
Can't wait to try multivariate then. That's the only way to go, sub 1.5 MA.
I think we all basically tried different things and we all got the same answer.
Yeah.
I love this session. This is amazing. I like that everybody tried different things. Cool. Any questions for David?
Well, just kind of a general question. Statistically, okay, so you guys are saying, you're not getting better, and I think you're eyeballing it. Well, how do you know? What kind of statistical test would you apply to your results to know if you've got a significant improvement? I noticed Dmitry got 1.3 on his ensemble method. I thought that looked pretty good, but you know, what do you do, you know, to know? Probably Robert, I figure, would know that answer, right?
I didn't quite catch the question.
Well, there's probably got to be some, like, in other words, you can eyeball it, you know, which is what I do, and go, oh, 1.3 is better than 1.5, but not that much better. 1.5 is not much better than 1.45, but there's, you know, statistically, how would you make that comparison is my question. And if you don't know, don't worry about it.
Are you asking, like, how would you know whether you're approaching some kind of lower bound?
No, between two tests, you know, between two results, how do you know if it is statistically significantly improvement?
Oh, if the improvement is statistically significant.
Or random, or, you know.
You could bootstrap, for example, right? You could pick different test periods, like, you know, a few months, and then try on that to see the distribution between the results, and then you could be confident that it's not by chance.
Okay, thanks.
I guess what you're asking is, you know, how different is 1.4 from 1.5? I guess that depends on your task, right? If this is a business problem, 1.3 from 1.4, maybe it's thousands of dollars, you know, at stake, but it's just a trivial task for us. So for us, all it means is that on average, one model is able to predict the mean temperature and it's off by 1.3 degrees plus or minus versus 1.4 degrees plus or minus. That's my understanding.
Right. But I think, like, statistically, normally wouldn't you interpret it as being, well, but that might be due to random variation?
Due to, is it completely different?
Or is it, you know, a real difference? But that's okay. That's okay. That's just me. Yeah.
No, I think the bootstrap approach that Dmitry suggested is the way to answer that. If you really want to know how likely it is that model X will beat model Y with different subsets of the same data.
Mm-hmm. Okay. Thanks.
Any questions for the group? Yeah, we posted the notebooks and they're on the slides. It's a good idea to go over them. And Dmitry, you have any more links for us that you'd like to share? Please let us know, especially about that data leakage. That was an interesting approach. Maybe if you had some fancy activation functions, I'll make sure I check them out as well. And Robert, I think one of your visualizations should be a painting, the one with the waves. I think Alan smiling. Cool. All right, everyone. Then next time we have a guest speaker. We'll be talking about distributed and parallel data science. We'll be looking at scikit-learn models. We won't be looking at TensorFlow, so slight deviation from our adventure path. But stay with us. Yeah, Aaron will be here next time, and he has given similar talks in the past, and I like the way he approached it. It'll be more on the code level, so he'll show us how to train a model with scikit-learn, the same machine learning model, and how would you pre-process data using, you know, regular pandas and pandas data frame, and how to use an open source project called Dask, which parallelizes all this pre-processing and training as well. So typically reduces the training time and evaluation time, and gives you way more time to focus your energy on other things. After that, we have another session that's still in the making. We will post it soon. But after that, we need to consider, you know, what is our next approach, and we have a long list of things we would love to consider, and you know, maybe we could tackle that as the next couple of weeks. Cool. Having said that, thank you, Dmitry. Thank you, David. Thank you, Robert, and thank you, everyone, for sticking with us. This was one of our longest sessions. Very interesting. I wish everybody a happy weekend, and hope to see you next time.
Thank you, George.
Thank you, everyone.
Thank you.
Thanks.
Thank you, Dmitry. Bye, everyone. Have a good evening.
Thank you.